All right. Hello, everyone. Welcome back. Hope you all had a nice, relaxing spring break. Um, and I'm just going to go ahead and get started. There's a couple presentations all smushed into one super mega presentation. So we'll get started with active remote sensing. So there are active sensors that send out a pulse of energy and detect the changes in the return signal. Most active sensors operate in the microwave portion of the electromagnetic spectrum, which makes them able to penetrate the atmosphere under most conditions. So LiDAR uses pulsed laser technology, which is light, to measure the ranges or the distances. The elevation surface is recorded in detail and shape of these features based on their measured distance from the scanning device. Laser returns are used to generate the cloud of points in X, Y, and Z space containing a series of attributes such as intensity, look angle, and a very accurate timestamp. LiDAR can then be used to model not only the terrain. LiDAR can then be used to not only model the terrain, but also the tree canopy, buildings, power lines, bridges, and everything else on and above the surface. In cars, LiDAR technology helps the vehicle sense and understand its surroundings. The technology uses laser pulses to create 3D mappings of its environment, including objects like buildings, roads, and other vehicles. This information is then combined with other data to ensure safe navigation. LiDAR tracks obstacles and vehicles to maintain safe distances. When using this data, it is able to identify road signs, traffic signals, and road markers for real-time hazard analysis. This technology is paramount in ensuring the safe and effective operation of autonomous vehicles. Synthetic aperture radar, or SAR, is a type of radar sensor that is mounted on an airplane or satellite and points sideways instead of on the nadir, which is down. The larger antenna will be the higher resolution. It is an active sensor that sends electromagnetic waves to the Earth's surface and receives the reflected signal or backscatter. And it uses microwaves and can penetrate through clouds, fog, dust, and smoke. Earth observation satellites are critical for monitoring and protecting tropical forests. This image is from our Sequoia satellite of Brazil, which demonstrates how our high-resolution SAR can provide a clear view of deforestation even when clouds obscure optical images. So on to the next, which is imagery interpretation. In order to take advantage of and make good use of remote sensing data, we must be able to extract meaningful information from the imagery. Interpretation and analysis of remote sensing imagery involves the indication and or measurement of various targets in an image in order to extract useful information about them. Some of these are energy source, radiation and atmosphere, interaction with the target, recording of energy, transmission, reception and processing, interpretation and analysis, and application. When you try to interpret features in an aerial photo or a satellite image, for instance, objects in developed areas or physical features in a natural landscape, you are like a detective searching for clues in the image to figure out what you're really looking at. Visual image interpretation is a process of identifying objects and features in an aerial image based on a number of distinct elements. Pattern is the physical arrangement of objects in an image. How objects are ordered can often help you interpret an image. A large array of cars set up as if for inspection on a parking lot around a relatively small building will probably be a car dealership. rather than some other type of shopping area. Evenly spaced rows of jet airplanes suggest a military base, while a haphazard arrangement of aircraft could be a group of statics on display at an aircraft or military museum. In the image on the slide, we see three main objects that are arranged in a diagonal line. Site association. The site deals with the location characteristics of an item, while association is the relationship of an object in an image to other nearby features in the image. For example, a football field itself has enough distinctive features to identify it, but the related phenomena you could see in the image, such as bleachers or the number and distribution of the seats, perhaps maybe the amount of nearby parking, would help determine if you're looking at a field used by a high school team, a Division I college team, or a professional team. Three objects are located in a large sandy area adjacent to a city, with that resembles roads leading to the objects. Size, which describes the length, width, and area on the ground of objects in the image. The relative size of objects in an image can offer good clues in visual image interpretation. For instance, the average length of a car is about 15 feet. If a car is present in an image, you can gain information about other objects by comparing their length with that of the car. You can tell, for instance, if a structure near a car is the size of a house or of a shopping center. The sizes of some features remain the same, whatever the image. If baseball diamonds or football fields are present in an image, elements in them can always be compared with other objects in the image to calculate their relative sizes. Comparing the size of the objects to the size of the buildings indicates that the objects are very large. Even the smallest of the three objects is larger than many buildings, while the largest is greater in size than many blocks of a city. Shadow, which is the dark shape cast by an object with a source of light shining on it. Shadow helps provide information about the height or depth of the objects that are casting them. For instance, in the Stratosphere Hotel example, the height of the tower itself is partially hidden due to the nature of being photographed from directly above, but you can figure out that it must be very tall because of the shadow it casts. Shadows can help you identify objects that are virtually unidentifiable from a viewpoint directly above them. From directly above, a set of railings looks like a thin, almost invisible thread around a park or in front of a building, and telephone poles look like dotted lines. However, if you look down at them from directly above late in a sunny afternoon, railings and telephone poles can be identified immediately by their shadows. Shadows cast by the objects indicate that not only are they tall, but they have a distinctive pointed shape at their top. Shape, which is the particular form of an object in an image. Distinctive shapes of objects in an aerial photo can help you identify them. A baseball field has a traditional diamond shape, racetrack has a distinctive oval shape, and circular shapes in farm areas might indicate the presence of center pivot irrigation in fields. Objects are square at the base and have pointed triangular tops, makes them pyramid shaped. Texture, which refers to the differences of certain shading or color throughout parts of the image. The texture of objects can be identified as coarse or smooth. For instance, different types of greenery can be quickly distinguished by their texture. A forest of trees and a field of grass may have the same tone, but the trees would appear rough in an image, while grass would look smooth. The texture of a calm lake looks very different from the rocky beach surrounding it. The area around the three objects is of very fine texture compared to some of the rougher textures nearby, especially to the right. Tone, which is the particular grayscale or intensity of the color in an image. The tone of an object can convey important information about its identity. In the Stratosphere Hotel example, the light blue color makes the swimming pool easy to identify. Similarly, a wooden walkway and a sandy beach have different tones that help you distinguish them from one another in a photo. The area around the three objects is much lighter than the area of rougher texture, and that area is probably a town or city of some sort given the pattern of the objects in this range. Given the tone and texture of the ground around the three objects, it's likely not smooth water or grass or concrete, therefore sand is a likely choice. Bringing all these elements of interpretation together, we can find three pyramids of different size, although still very large, in a definite fixed arrangement in sand near a busy city. All of these clues combine to identify the Great Pyramids of Giza just outside Cairo, Egypt. Aerial images often contain clues that help to identify the objects they contain, or at least narrow down the options to a handful. Some brief research using collateral material can help nail down the identification. And these are the five, or the different types that we just walked through. 7. So for image classification, this refers to the task of extracting information classes from a multi-band raster image. Along with military surveillance and weather forecasting, the primary use of remotely sensed image data has been to monitor land cover to inform land use planning. The term land cover refers to the kinds of vegetation that blanket the Earth's surface or the kinds of material that form the surface where vegetation is absent. Land use, by contrast, refers to the functional roles of the land plays in human economic activities. For instance, to perform a supervised classification of the Landsat thematic mapper data shown above into two land cover categories, vegetation and other, you would first delineate several training fields that are representative of each land cover class. The illusion below shows two training fields for each class. However, to achieve the most reliable classification possible, you would define as many as 100 or more training fields per class. The training fields you defined consist of clusters of pixels with similar reflectance or emittance values. If you did a good job in supervising the training stage of the classification, each cluster would represent the range of spectral characteristics exhibited by its corresponding land cover class. Once the clusters are defined, you would apply a classification algorithm to sort the remaining pixels in the scene into the class with the most similar spectral characteristics. One of the most commonly used algorithms computes the statistical probability that each pixel belongs to each class. Pixels are then assigned to the class associated with the highest probability. Algorithms of this kind are known as maximum likelihood classifiers. The result is an image like the one shown below, in which every pixel has been assigned to one or two land cover classes. Sorry, one of two, not or. The image analyst plays a different role in unsupervised classification. As an image analyst, you would not define training fields for each land cover class in advance. Instead, you would rely on one of the family of statistical clustering algorithms to sort pixels into distinct spectral classes. You may or may not even specify the number of classes in advance. Your responsibility would be to determine the correspondences between the spectral classes that the algorithm defines in the functional land use and land cover categories established by agencies like the U.S. Geological Survey. The example that follows outlines how unsupervised classification contributes to the creation of a high-resolution land cover dataset. Improved image classification allows us to extract features, which we can then measure, analyze, and compare over time. Pixel-based image classification considers each pixel individually and does not consider any information from neighboring features. Each pixel is assigned a class independent of its spatial context. This type of classification works well with coarse spatial resolution raster data where real-world features are difficult to recognize. Object-based image classification uses a process called segmentation to group neighboring pixels into segments or objects based on similar spectral and spatial characteristics. Unlike pixel-based image classification, classes are assigned to segments rather than the individual pixels. Object-based classification works well with fine spatial resolution rasters. The reason is that the meaning image objects, not a single pixel, can offer important semantic information which is necessary to interpret an image. Object-oriented image analysis techniques are a perfect classification approach, especially for high-resolution imagery. When you have a low spatial resolution image, both traditional pixel-based and object-based image classification techniques perform well. But when you have a high spatial resolution image, OBIA is superior in traditional pixel-based classification. Image segmentation techniques range from simple, intuitive heuristic analysis to the cutting-edge implementation of deep learning. Conventional image segmentation algorithms process high-level visual features of each pixel, like color or brightness, to identify object boundaries and background regions. Machine learning, leveraging annotated datasets, is used to train models to accurately classify the specific types of objects and regions an image contains. Being a highly versatile and practical method of computer vision, image segmentation has a wide variety of artificial intelligence use cases, from aiding diagnosis in medical imaging to automating locomotion for robotics and self-driving cars to identify objects of interest in satellite images. Land cover relates to the type of feature present on the surface of the Earth. Land use relates to the human activity or economic function associated with a specific piece of land. Raster data with 30-meter spatial resolution derived from Landsat imagery uses an unsupervised classification to generate 100 spectrally distinct pixel clusters. Image analysts at USGS assigned each cluster to a class. The steps for creation is pre-processing, unsupervised classification, and accuracy assessment. This is an image of the steps described in the last slide, and how we can go through and assign the different features. One of the key applications for deep learning in GIS is land cover classification. Land cover classification involves distinguishing different types of land cover, such as urban areas, forests, water bodies, and agricultural fields from satellite imagery. Traditional methods often struggle to accurately differentiate between closely related classes, such as different crop types. Deep learning, however, can handle such complexities with ease. With its capability to learn from vast amounts of data, it can discern subtle differences in land cover types and classify them accurately. These classified datasets can be incorporated into a GIS, contributing to a wide range of applications, from urban planning to environmental conservation. Pearl is the Microsoft Planetary Computer Land Cover Mapping Platform. It combines state-of-the-art machine learning technology, open datasets, and scalable computing from Microsoft Azure to improve LLULC mapping workflows. This version of Pearl has 2 starter models. While these models have been trained primarily with data from the East Coast of the United States, they should be a good starting point for LULC mapping throughout the country. The main difference between these models is the number of base classes. The platform can map up to 9 LULC classes using the 9-class model. These classes are water, emergent wetlands, tree canopy, shrubland, low vegetation, barren structure, impervious surface, and impervious roads. The base training data for each of these models comes from the Chesapeake Conservancy. Run, model, retrain, run again. After submitting retraining samples, the analysis panel will populate with metrics on class distribution and class F1 scores. This is possible because the subset of the retraining samples are held out, so the retrained model can be evaluated against those samples. Use the analysis to compare your expected understanding of an area's land cover classes with the returned results. The F1 score is the harmonic mean of precision and recall. Precision is the percentage of guesses that a model makes that are correct. Recall is the percentage of true positives that a model captures. At a pixel level, we're comparing if the predicted land cover class matches the ground truth land cover class. The global F1 score in the model metadata card is weighted. F1 score, so classes that occur more often, will have a greater weight in that value. Interpreting this global score within the context of the F1 score performance for each individual class will give a more complete picture of model performance. The simplest is image classification, in which the computer assigns a label such as cat or dog to an image. This can be used in GIS to categorize geotagged photos. One of the images above has been classified as a dense crowd. This pedestrian activity classification can be used for pedestrian and traffic management planning during public events. With object detection, the computer needs to find objects within an image as well as their location. This is a very important task in GIS, finding what is in satellite, aerial, or drone imagery, locating it, and plotting it on a map. This can be used for infrastructure mapping, anomaly detection, and feature extraction. Another important task in computer vision is semantic segmentation, in which each pixel of an image is classified as belonging to a particular class. Is instance segmentation. You can think of this as a more precise object detection, in which the precise boundary of each object instance is marked out. Instance segmentation can be used for tasks like improving base maps. This can be done by adding building footprints or reconstructing 3D buildings from LiDAR data. Finally, an amusing example, just to show that even with regional convolution-based classifiers, computer vision is still really hard. Fortunately, the smallest people at Google, Facebook, and so on are working on algorithms to be able to determine the difference between dogs, cats, and different breeds of dogs and cats. So those of us interested in remote sensing can sleep easy at night. With machine learning, a system is taught how to interpret information based on specific inputs. Machine learning models require human involvement to manage the model inputs and adjust them when necessary. With deep learning, a system is taught what to look for from the data to conduct the desired analysis. This task is accomplished using neural networks, which mimic the ways in which a human brain processes information. These neural networks pass information through multiple layers to filter and classify data based on recognizable patterns. In working with satellite imagery, one important application of deep learning is creating digital maps by automatically extracting road networks and building footprints. Imagine applying a trained deep learning model on large geographic area and arriving at a map containing all the roads in the region, then having the ability to create driving directions using this detected road network. This can be particularly useful for developing countries that do not have high quality digital maps or in areas where newer developments have been built. So now we are on to disaster mapping. So this is a image of the U.S. based off of the National Weather Service, and how different areas manage the weather. I do have a link here that can give us a little bit more information. So this is the National Risk Index, and I do highly recommend, if you guys have some time, to go check this out on your own. But it basically goes through and gives different areas a value based on how at risk they are for national disaster. Oops, that's not what I wanted to do. That is the link we were just on. So move on to the next one. The National Risk Index is a data set and online tool to help illustrate the United States communities most at risk for 18 natural hazards. It was designed and built by FEMA in close collaboration with various stakeholders and partners in academia, local, state, and federal government, and private industry. The Risk Index leverages available source data for natural hazard and community risk factors to develop a baseline risk measurement for each United States county and census tract. Social vulnerability is the susceptibility of social groups to the adverse impacts of natural hazards, including disproportionate death, injury, loss, or disruption of livelihood. As a consequence, enhancing risk component of the National Risk Index, a social vulnerability score, and rating represent the relative level of a community's social vulnerability compared to all other communities at the same level. A community's social vulnerability measures its national rank or percentile. A higher social vulnerability score results in a higher risk index. Community resilience is the ability of a community to prepare for anticipated natural hazards, adapt to changing conditions, and withstand and recover rapidly from disruptions. As a consequence, reduction risk component of the National Risk Index, a community resilience score and rating represent the relative level of a community's resilience compared to all other communities at the same level. A community's community resilience score measures its national rank and is inversely proportional to a community's risk. A higher community resilience score results in a lower risk index score. During disasters, it is critical for response effort to create and maintain situational awareness. Collecting and sharing data mainly is a slow method where the obtained data can easily become out of date. GIS in this case can help to provide mapping and analytics that allow to obtain what is happening in real time with brief descriptions that can create immediate responses. The system can enable emergency response teams to quickly intervene with real-time data from various sources, such as satellite imagery, weather, data, social media feeds, and sensor networks. Affected areas can be identified, population density can be estimated, evacuation routes can be found, and response efforts can be coordinated with the use of information in situation maps. In the post-disaster period, it is important to understand the impact of the disaster and accurately deploy resources to achieve community recovery. Damage assessment plays a key role for the road to recovery. Damage assessments aid in calculating the number of homes damaged, families uprooted, short-term casualties and injuries, and damaged infrastructure. Additionally, it facilitates the restoration of communication so that it functions more effectively going forward, or lays the groundwork for an emergency communication network that can come online right away in the event of a crisis. This is just a couple examples. Nearly 60% of buildings in the United States are located in a disaster hotspot. If a disaster were to strike your home, what is your emergency go bag? Do you have extra food, water, clothes? What about OpenStreetMaps? OpenStreetMaps has been used by disaster responders and for resilience efforts around the globe formally since 2010, largely led by humanitarian OpenStreetMaps team. While the direct impact may seem clear in parts of the world where geospatial data can be scarce, mapping in OpenStreetMap can be just as critical for resilience and response here in the US. Beyond direct disaster response and community resilience efforts, OpenStreetMap has become a significant tool for researchers and modelers to predict and understand how disasters will impact us in a rapidly changing climate. Models like Flood Factor use OpenStreetMap for building footprints to help identify flood risks across the United States. Additionally, OpenStreetMap datasets such as emergency facilities can be used to understand equitable access to services. So that is the entire lecture for this week. Let me just switch over. So yes, that is everything I have for you guys for this week. There is a new assignment up for the week. It'll be due on the 28th, so next Friday. Also, if you need or think you might need or are just interested in doing the extra credit, it is due tomorrow, the 18th of March. This is going to be the only extra credit opportunity for the entire semester. So if you're worried you might need it or just want to be on the safe side, I highly recommend doing it. It should not take too long. So definitely check it out. And that is what I have. If you have any questions, feel free to reach out. Otherwise, I will see you guys next week. Have a good week.